Okay, so our first topic is going to be limit. So we'll slightly go back uh, to the idea of straight line for a while, and then we'll um, come back to limit. Um, and for that, I want to share the screen of my iPad as well. Let me do that. Mm, okay. Okay. Yeah. Oops. Why is it not? Oh, it's creating an echo. I should leave them. Okay. Yeah. So limit. So what do you understand when you first hear this word limit? What comes into your mind? I mean, not mathematically. It doesn't necessarily mean it has to be mathematically. What's the first thing comes into your mind when you hear this word limit?
The
Anyone?
endpoint of something.
Endpoint of something. Okay. Anyone else?
A maximum.
Maximum. Okay. It doesn't necessarily be uh, maximum. Okay. So, in the chat, I can see how far something can go. Uh, okay. Yeah. 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 I think that makes sense. Okay. So I can understand why did you say maximum? Yeah. Maybe, for example, if you go to Walmart, they might say the limit is two, let's say two bottles of milk, 2 gallons of milk per person. So that means the maximum you can take is two. So yeah, I think the word maximum goes with this as well. Very good. Anyone else?
Yeah, it's how maximum or how many an object can go.
Mhm. Okay, yeah. I think when you say limit, that means you are somehow restricting it, right? You are trying to restrict something, and you are trying to find a value which you can't exceed or which you can't go below. You can't really go below that, or you can't go or you can't go uh, past that. I mean, you have to be within that value, right? So in maths, when we say limit, we actually mean, if you well, if I rephrase it in English, if you move from your left and if you move from your right, you are actually reaching to that same place. I mean, if you have a limit at a particular point, that clearly means if you move from your left and if you move from your right, you'll reach the exact same place. We'll see more of this once we progress. You will see more examples of it and why does it make sense as well. So before that, we want to, as I said, we want to uh, go back to some previous concepts, and then we'll come back again to limit. Okay, so first thing is how to graph. If you remember how to graph a function or how to graph um, an equation, maybe, or rather an expression. So for that, uh, if you see this figure, oh, sorry, I need to scroll down. Yeah. So let's say my function is negative 16t squared plus 96t. Okay. So that's my function. And if I say, can you graph it for me? Who can do it for me? Is there anyone who can't do it? If you can't do it, there is no shame in that. We can discuss more and more, and uh, probably it will make more sense. But if you can't do it, just let me know, okay? Is there anyone who can't graph it? Can't graph a function like this? For example, like this one. 16t squared plus 96t.
Yes.
Everyone is okay with this? All right, looks like.
Yes.
All right. So if you're trying to graph a function like this, what you would do, we first pick up points randomly. If nothing is mentioned, we can pick up any point as we want. So we pick up a point randomly and we plug it back. Plug it back where? Plug it back into the function, right? Oh, meanwhile, I think I forgot to mention it. So only for today and tomorrow, I think I won't be able to use my, let me see, I think I won't be able to use my iPad uh, because I'm actually currently out of Laramie for some obvious reasons. I'll arrive Laramie tomorrow. So from the day after, from 26th, I'll have my own setup, my own laptop and iPad. So then I'll be able to share my screen, or share the screen of my iPad. Now I'm using a different laptop, which is not mine, obviously. So I don't think I am able to share the screen of my iPad using the Air share or something like that. I'm not sure whether we have anything like that with the Windows one, but I'm familiar with the Mac version. I mean, I use the Mac. So do you know, can I share the screen with the Windows as well? Is there any expert? I mean, someone from the computer science maybe? Because in the Mac, I think I can easily share the screen of my iPad without even joining Zoom. I can just share the screen. Is it possible with Windows as well? Anyone?
On Zoom or what?
Yeah, on Zoom, yeah.
I have a Windows and it lets me share, so yeah.
Okay, I think I should
I
be able
think.
to share. Let me just check. Yeah, I think it will be possible. Just give me a second. Let me connect my iPad. Ah, no, it says a plugin is required to share an iPad. Yeah, as I said, since I have a Mac, it doesn't require any plugin. Anyway, yeah, I think I'll start doing that from 26th. Sorry about that. All right, so let's go back to the function. So if you take a point randomly and then plug it back to the function, you get a corresponding functional value, don't you? And then you can graph it as a point with x and y coordinates, right? There's something in the chat. Is there a way you can put the slides in full screen so it's easy to see for us? I guess it's in it's already the largest I can get. Probably, let me see. Does it help if I zoom it more? Maybe I'll miss some of the parts.
Other way, like if you minimize it, it doesn't minimize anymore.
Should I minimize it?
Like you were pressing the plus button. If you press that, like the like magnifying glass one. There, nope, there you go. You just had it. Press it. Yep, right there.
I see. Okay.
Yeah, that's fine.
All right. Yeah. Okay. Okay. Perfect. Okay. So we have a couple of points with x and y coordinates. I mean, for this particular function, it will be s and t, right? Because we are taking the values of t randomly. Can you see the cursor?
Yeah.
Okay. So it will be the value of t which will be taken randomly, and then we'll have a corresponding functional value for S. So we have a couple of points with S and T and S, rather, T and S coordinates, as you can see. And if we can just graph these points and join those, we should get our function, right? That's the basic idea of plotting a function, by the way, right? Okay, now we can use this method to graph any point, or rather any function, and then we can actually go to this to find the slope. Now, the first thing I want to know is, let's forget about this problem. What do you understand when you hear the word slope? Again, I'll be doing this every time. Whenever I you'll see a new term, I'll ask you, what do you understand by that? I mean, in English, not mathematically. So again, what do you understand?
It's how steep something is.
Sorry.
Yeah.
Yeah, would you please repeat it?
I said as a slope is like how steep something is.
Okay, yeah, anyone else?
Yeah, slope is the change of dy over dx, or
Okay,
is the
so
change
that's
of y value to x value. That's mathematically.
yeah, I understand. That's mathematical. Yeah. Anyone else? Rise over run. Okay, that's very good. Although it's
It's an
mathematical.
incline.
It's what? Sorry.
It's like the incline.
Incline.
line.
Okay. Okay. Right. So yeah, I think you have already mentioned all the mathematical definitions as well. Rise over run, the changes in y over the changes in x, something like that. I mean dy over dx. All right. So yeah, slope will actually give you an idea how much your functional value will get changed if you just change your value by any margin. Maybe, yeah, you can actually change it by any margin. How small is it, how big is it, doesn't matter. If you just change it, if you change the t value for this particular example, if you just change your t value, how much the s will get changed. So the slope gives you an idea. And this is really important because you can't really graph all the points. You don't, I mean, you don't really need all the points to graph a function, right? And for a larger value or for a really smaller value, you don't need to know all the values. So what you can do, you find a formula which gives you this particular change. I mean, if you just change your t by 1, how much the s gets changed, or vice versa. I mean, if you just change your t value by -1, then how much now the s will be, the new s, the functional value of s will be. So slope, the idea of slope is really, really important. And you will see I'm using this word slope probably each day, at least once, maybe more than that. Okay, now, how can you define it? Okay, I think two of you have already mentioned it, that it's the change of y over the change of x. That means you're trying to find well, obviously for that you need to have at least 2 points. Can you see that? That's the beauty of slope. I mean, you are trying to find the change, so that means you need to have an end point and a starting point. Otherwise you can't find the change, right? So you actually have 2 points. So for example, in this graph, you can see we have 180 and 144, right? That means the t value is 1 and the corresponding functional value of s is 80. And for the next one, the t value is 3 and the corresponding functional value is 144. So we already have two points. And now we can use this to find the slope, which will in future help us to find how much the change in t will bring changes into s, right? Okay, so now let's hide the value of s. Only keep an eye on t. So the first value of t is 1, right? And the second value of t is 3. What's the change in that? Can you see that? Don't look at the graph, just try to use your intuition. You started when t was 1 and you ended where t is 3. So what's the change in t after you finish?
It's 2.
2. And
3
how
minus 1 equals 2.
yeah,
Change is
exactly.
equal to 2.
Oh, sorry, I think I missed out the last one. Did you say anything?
Yeah, change in t is equal to 2.
Excuse me. Yeah, right. So again, I know it's some basic stuff, but to find the change, the general idea is to subtract the starting point from the end point. Okay, that's the general idea. So if we subtract 1 from 3, we get 2. So the change in t is 2. Now we want to find the change in s, right? Because we know for the slope, we need to have the change in the y-axis, which is s on this occasion, over the change in the x-axis, which is t on this occasion. Doesn't matter what our variable is, as long as we know what is which variable we have in the x-axis and in the y-axis, we should be doing fine. If it's been represented graphically, of course. All right. Now, let's see the change in y, I mean, change in s on this occasion. So the first functional value we have is 80. And the second functional value is 144. So what's the change in s? Again, we'll use the same idea, right? We'll subtract the first functional value from the ending one, I mean from the second one. So if you subtract 80 from 144, you get 64. Can you see that? Okay, now we have the values, we have the change in t, we have the change in s. So slope, as I said, is basically the change in the functional value or the y-axis or whatever we have in the y-axis, or we might rephrase it, the change in the dependent variable. I'll come back to it. What does the dependent variable mean, if you're wondering, over the change in x-axis or whatever we have here, or the independent variable. Now, is there anyone who wants me to discuss what is an independent variable? I'm more than happy to do that. Is there anyone who is slightly confused, or if everyone is okay, I'll move on. I'll proceed from here. Everyone, does it make sense? This word, I mean, independent variable. I can't see anything in the chat. Oh, I have one thing in the chat. Yes, okay. So by yes, did you mean that it makes sense, or do you want me to discuss discuss what it is?
I think it makes sense.
All right. Okay. So yeah, let's move on. If you are confused, then just let me know. Okay. All right. So now we can just find the ratio of these two. So the change in the y-axis, in the dependent variable in the functional value, whichever you whichever phrase you want to use, is the change in that is 64, right? We have already subtracted 80 from 144, and we have got 64. And the change in the independent variable, or t on this occasion, is 2. So if we just take the ratio of this, we get 32. Obviously, if you consider the unit, it will have a certain unit. On this occasion, we have considered time as the independent variable, and the distance in feet, by the way, as the dependent variable. So you can clearly see the unit will be feet per second. Okay, so now what does this mean? This is really important to understand. What does this signify? Okay, so this 32 feet per second signifies if you just change your elapsed time, but change your elapsed time by just 1 second, you will move forward by 32 feet. If you spend 2 seconds, you will go 64 feet, and so on and so forth. So this is really important. So if I say how long will you go in 10 seconds, you can just, if you just have this value, you can straight away calculate it, and you don't even need a calculator, right? If I say how long will you go in 10 seconds, can you say that? Can you calculate it by just eyeballing this? Anyone?
Yes, can you repeat that?
Sorry.
Can you repeat the explanation?
Oh yeah. So I said, if you spend 10 seconds, how long will you go? Or not how long, how far will you go if you have a slope of 32 feet per second?
320 feet, right?
Exactly. Yeah, as I said. So this gives us an idea. What does the change in the independent variable brings, or bring rather? So this is 32 feet per second means for each second you will go 32 feet. So when I say you have spent 10 seconds, that means you will actually go 320 feet. Now, does it make sense? Because
Yep.
yeah, because the idea of slope is going to be really, really important. If you are somehow still confused, no worries, I can rediscuss it. But just let me know, okay? If you are slightly confused that whether you ask it right now or maybe later in my email, that's perfectly fine. Whichever you like, whichever format you like, either in the Zoom meeting or after we finish, that's perfectly fine. Okay, just let me know for any topic, for anything. If you're confused, if you want me to rediscuss, or if you are still not convinced by however I try to convince you, just let me know. I'll try different ways to convince you. Okay, all right. Okay, what else? Yeah, you might remember the other way. I guess someone in the chat had it as well. Yeah, Abby had it. Rise over run. So if you're eyeballing a graph, the slope is basically rise over run. Now, what does the rise mean? Rise means going this, right? Going vertical. No, that's just the other way of rephrasing rise. Just rise from here, right? And run means you can't really run vertically, right? You can run only horizontally. So run means in this way, right? And rise it in this way. I wish I could use my iPad. I'm sorry about that. So from 26th, I think I'll be able to use this in a better way. Anyway, so rise over run means this is your run, right? And this is your rise. So if you take the ratio, rise over run, you can see you get the same thing. If you want to remember this way, that's absolutely fine. You can remember it this way. But the mathematical definition is a change in y over the change in x, where y is definitely the dependent variable or the functional value, and x is the independent variable. Okay. Any question? Anything you want me to rediscuss? No questions at all? Okay. So, maths is a boring subject. I can clearly feel, because I'm a student of math, so I can understand it's a boring one. So what I want you guys to do to make this discussion more lively and perhaps just a little bit more interesting is to interact. If you interact with me, then probably it will be more lively. Okay, so if I ask questions, you can answer it by unmuting yourself, or even you can unmute yourself and ask questions if you have any. And this way we can probably make it more interesting, and it will not become really boring. Okay. All right. So let's move on. Okay, so yeah, let's quickly do this one. So don't look at the slope in the first place. Let's try to do it by just eyeballing the graph. Okay, let me hide the answer. Okay. All right. So that's your graph, and you have 2 points. The first one is 180, and the second one is 128. Okay. So from these 2 points, can you calculate the slope? That's the first question. I don't know the answer. Is there anyone who is confused how to calculate the slope from these 2 given points? Okay, something in the chat. Okay.
The answer is 52.
No, you don't need to calculate it. I'm just trying to see if there is anyone who has a confusion, who has confusion.
Oh, sorry. I think you are giving us the lesson to work it out. I'm sorry for that.
No problem. All right, so from these 2 given points, we want to calculate the slope. So what should we do? We know the definition is the change in the y coordinate, right, over the change in the x coordinate, right? So what's the change in y coordinate? The change in y coordinate is 128 minus 80, so that's 48. And the change in x coordinate is 2 minus 1, which is 2.
Oh, sorry. I think you said it's 180. I don't know, it's 80. The first one, which is 1,8.
1,80, yeah.
Yes, I think it's 180. I don't know, it's 80.
Oh, sorry. Yeah. Sorry about that.
So the change of y should be 128 minus 80.
Right, yeah. And the change of x is 2 minus 1. So now we know the changes. What else we need to do? We just need to take the ratio. So 48 from the change in the functional value and 1 from the independent variable. So the change, or rather the ratio of this is 48 over 1, which is 48. And this is actually our slope. Here you go. The slope is 48 over 1. Any question from this? This is just the beginning, by the way. So if you might have two opinions, that why am I spending too much time on this? Or rather, the second one, what the hell is that? So whichever it is, you just let me know, okay? I'm more than flexible to make adjustments, okay? If you think I'm going too fast, let me know. I'll try to slow it down. If you think I'm really going slow, I'm going really slow, I can probably go faster as well. Okay, just let me know whichever you think can be done to make this, or rather bring more and more, bring out more and more from this class, I would say. Yeah.
I mean, I think it's a good review. So Rise Over Run is not a bad thing to review, I suppose.
Yeah, I think the first week is mostly about the review. Not the entire first week though, but yeah, I know you, most of you, at least half of you, maybe more, maybe all of you already know the stuffs, but I think spending time on this is worth it, because you are starting a new semester. If I start with something really difficult, that will blow your mind. So I'd rather start with something easier and then go for the potential more complicated ones as well. Okay, so all right, so it's 12:04. I mean, sorry, 10:04, and we have a class until 11. Is it, or 11:05?
11:05.
11:05.
Okay, so what I planned, I have planned to take a break of 5 minutes after the first hour, or rather just before the first hour. So each day we'll take a break at 10:05 and we'll come back at 10:10. Is that okay?
Yep.
Okay, so you'll stay online. I'll stay online as well. I'll actually stay in the Zoom meeting. I'll not go anywhere, but just have a little bit rest. And if you want to have coffee or something like that, just go for it, because 2 hours talking 2 hours at a stretch is really stressful. Okay, so let's take a break for 5 minutes. Don't go anywhere. I mean, just be in the Zoom meeting, and I'll see you in 5 minutes. Where is my iPad? Okay. Oh, something in the chat. Hi, I just wanted to remind you that. Oh, that's perfectly fine. That's perfectly fine. It's okay. No problem. I'll return to Laramie tomorrow, so I'm having problems with the time zones as well. So I have to I literally have to set up reminders for each thing so that I don't miss out, because that's the last thing I want to do, is to miss out an appointment with someone. For example, I have a meeting with my professor at 3 p.m. Laramie time. So I'm currently in Michigan, so I set up an alarm. First, I set up an alarm at 3 p.m. and then I remember, oh my God, I'm going to miss out then. I mean, it will be too early, but it will be a complete mess. So hopefully, if I return tomorrow, things will get much better.
On Pearson, we paid for like the inclusive access or whatever. But
Mhm.
how do we get our access code so that we can do the homeworks and
Okay,
stuff?
so yeah, I'll make an announcement about it. So about purchasing the book and having the access and all that. To be honest, I am not the person you should ask, because I'm teaching it for the first time. Um, the best person to answer this is going to be Eric Moorhouse. I'm actually going to uh, provide you provide you all with the email address of his in the announcement soon after we finish today, hopefully, because he's the course coordinator. He actually takes care of all these things. Hopefully, he will be able to answer you better, because I guess calculus is uh, taught by 4 person in the fall, 3 in the spring, and 2 in the summer. He is the coordinator of all those courses. So I generally believe that he has the idea how to get this access and all that.
Okay,
Uh,
thank you.
yeah. So the good thing for you guys is, until everyone has their answer or has the solution, I'll not give you any homeworks, because you need to log into my MATLAB to complete your homework. So hopefully all of you will have access by the end of this week, but I'll not give you any homework before that.
Anyone that, I'm sorry, Mr. Haig,
Yeah.
anyone that automatically register for the course, the code will be automatically sent to the student email. So I'm currently receiving it on my email right now.
I didn't understand. Would you please repeat it?
What I'm saying is the code,
The
the
access
course
code?
code, the access code will be automatically sent to every student that register for this course this summer.
So you are saying if you buy the book, the code will be emailed to you automatically?
Yes, if you enroll for this class, the
I
code will be
see.
automatically sent to your email, your school email. I am
I
receiving
see.
my own right now.
Ah, okay. Yeah.
Yes, so
Okay,
that
I
you can
enrolled and paid, but I can't find it. What's like the email?
then you email
title?
them back that you can't find it, they will send it to you.
Did you
Oh.
get the email when you paid, or when did it come in? Because I paid.
When
like,
you enroll for the course, you get the email directly. When you enroll for this course, they will see that you have already enrolled. So every student that enrolled, they will send the code to each student differently to their email. So you should be receiving it.
Weird.
All right, let's start again. So yeah, if you have gone out for a break, we are actually having a discussion about the access to my MATLAB. and I know some of you are struggling with that. So what I'll do is I'll do both ways. I'll ask the course coordinator, Eric, how to resolve this. And if he has any suggestions for me, and obviously I'll give you the email address of Eric as well. In the keep an eye on the announcements. If you ask him, hopefully he will be able to give you a better solution. I know some, not all of you have the same problem. There could be some different issues, but if you let him know, I believe he will be able to resolve this situation. But I'll ask him myself as well, because I need to see whether I can do anything which makes your life easier. Because this MyMathLab, I know this, first of all, you need to pay for it, and then you need to, wait for some time to get the access. So in the previous semester, in the spring, I mean, I used MyOpenMath, which is free to everyone, which was a good thing. But the problem was the interface was not that easy. Most of the students, even myself, we actually struggle to navigate that. Whereas I guess MyMathLab is easier to navigate, but again, you need to pay for it anyway. That's how it is. Can't help anything. All right, so we are back to our discussion, and we want to go to the next topic, which is the secant line. Okay. Now the slope has one other name as well. In maths, we often rephrase it by the tangent line. I mean, the slope, you can get the slope, you can't really say the slope is the tangent line, but if you draw a line which goes through the slope, I mean, the point, that straight line, it will be a straight line for sure. That straight line can be rephrased as tangent line. Or in other words, if I say it in the other way, in the other direction, if you draw a straight line which touches the graph at only one and only point, then that line is called the tangent line, and that point gives you the slope. For example, okay, so we don't have a, that's why I didn't mention in the first place. Yeah, we don't have a figure of it. Let me see if we have anything on the next page. No, we don't. Oh, here it is. Yeah, the tangent line. So eventually we'll come to it. Okay, that's fine. All right. So let's go back to the page where we were. Okay, this one. Yeah, the secant line. Now, what is a secant line? So the secant line, again, you'll have the change in the x-axis and the change in the corresponding value, that means the y-axis, and then we'll take the ratio. We'll say that it's the it gives us the secant line. I mean, this line. Can you see this line, the greenish straight line which goes through this bluish circle? This straight line is called the secant line. Now, why is that? So if you draw a graph, and if you can, I mean, if you have a graph already, and if you can draw a straight line which goes through 2 points of the graph, then that straight line is called the secant line. You can see the black curve is the graph of our function. This black curve, you know, like the what it looks like. Anyway, yeah, the black curve. I can't really resemble anything which I can imagine. Anyway, yeah. So this black curve, and I have 2 points, this bluish 2 points. If I can join these 2 points, I get this greenish line. Not exactly green anyway, but yeah, this is greenish line. So this line is called the secant line. That's how we define a secant line. And you'll soon see if these 2 points merge into each other, if this 2 point comes really close to each other. In maths, we say it actually merges to each other. I mean, not merges, it merged to each other. Then we call it the tangent line. That means you draw a line which actually touches the graph at most 1 point. I mean, at one and only point, then it's the tangent line. But if it goes through 2 points, then we say it's the secant line. Okay, so that's the secant line. We don't need this one. Yeah, okay. Now, how can we go from secant line to tangent line? Now that's what we want to say. I want to see rather. As I said, if these 2 points come really close to each other, I mean the difference, as you can see, this is the difference of 2 points, right? I mean, we have the difference of t, we have the difference of the corresponding value as well. And now if the difference is getting smaller and smaller and really teeny and tiny, then we actually can estimate it better. We can estimate anything better if the tolerance level is really small. If you do computer programming, if you're trying to find a solution, often you'll see you need to provide them a tolerance level. That means how big the error could be. So the smaller you take the error, the better you get the estimate, don't you? So to get better estimation from this graph, what we do is we take the difference really small. And how small can you go? Okay, we'll soon see. So what we do now is we start bringing the differences to really close to the initial one. So for example, we started with 1 and 2 in the previous example, right? Where is that? Yeah, here we go. So here t was 1, and the final t, the final value of time was 2. We started with 1 and finished at 2. Now you will see, we'll try to close it down. We'll try to change the differences to a lower value. Here's the first one. We started with 1 and 2, as you can see, and then we change it to 1.5. Okay, so now we'll be actually considering 1 and 1.5 instead of 1 and 2, like that we have done in the first one. So now we'll take this one. The change of time will be 1.5 minus 1. Why is that? It's the same reason as this. Instead of 2, we are now considering 1.5, right? It's somewhere here. As you can see the cursor, it's somewhere here in between. It should be at the middle point, but it's difficult to eyeball the middle point anyway, but it looks like it's somewhere here, right? The middle point in between 1 and 2, 1.5, right? So now the time difference will be 1.5 minus 1. And obviously we need to take the corresponding functional value as well. So it will be the functional value at 1.5 minus the functional value at 1, right? It's the value of S. It's a functional value. It's a corresponding value. And if we calculate it, let's go back to the function real quick. I wish I had the iPad. I actually have it, but I can't really screen share using the mirror of screen mirroring of Apple. So that would have been more convenient. Again, I apologize for that. Okay, so that's the function. And now we have t as 1.5, right? So it will be negative 16 times 1.5 squared plus 96 times 1.5. Can you calculate it for me? So t is 1.5. So it's negative 16 times 1.5 squared plus 96 times 1.5. If you calculate it, and if you trust me, you will get 108. Can you verify it for me? Anyone?
Yes.
Did you get 108?
Yes.
Okay, is there anyone who has a different result for S 1.5? I mean, if you plug in 1.5 in the function, have you got a different result than 108? Anyone? Okay, I think it's fine. Okay, and S1, the functional value, we already know it, that's 80. So the difference will be 108 minus 80. And if you take the ratio, it will be 56 feet per second. So you can see the estimation is getting better, right? It was 48, now it's 56. And now instead of 1.5, if we change it to 1.1, that means you can see the difference is really, really, really small. We started at 1 and now we're considering 1.1. So the difference is really, really small. So now we'll follow the same procedure. We'll take the difference 1.1 minus 1, and we'll take the get the corresponding values as well. So we'll plug in 1.1 in place of the t's, and if you trust me, or if you trust the book author, you will get 86.24. Now can you verify it for me? Can you actually get 86.24? Just use your calculator.
Yes, correct.
Plug in 1.1 in place of the t. For your convenience, let me show the function again. Yeah, here is the function. Just plug in 1.1 here and 1.1 here. Just plug in 1.1 in place of the t.
The answer is correct.
Okay, perfect. Okay, so now the ratio will be 62.4. Again, it got better. We had 56 for 1.5. Now we have 62.4. You can see that our estimation is clearly getting better as we are decreasing the difference. So the intervals are getting shrink and we are getting a better result. Okay, now how does it help? Okay, now if I say, can you tell the instantaneous velocity, I mean, we are definitely working with velocity, right? Because t is in time, t stands for time, and s gives you the distance covered um, corresponding to that time. So s actually, since s is the distance, and we know that a definition of velocity is distance over time. So this is actually giving us velocity. Can you see that? Especially if you have some physics courses before, if you had it before, you already know the definition of velocity, which is distance over time. And all of these, you can see, even by eyeballing the unit, you can see it's the velocity, right? Because the unit of velocity is the distance over time. You can see feet over second actually signifies velocity. So if I ask from all this calculation, or by doing it repeatedly, by shrinking the interval even more, can you tell me what's the instantaneous velocity at t equals 1? And the
I
answer is
think,
yes,
I
we can.
think,
Yeah, sorry.
yeah, I think the velocity is increasing because on the point one, it is 48 feet per second. It rises to 56 and now to 62.4.
Yeah, you're right. It's definitely increasing. Okay, so the first question would be again, what does this instantaneous word mean in English?
It means something that happened in an instant time.
Exactly. We're looking for something instant, which is happening instantly, right? At that particular point. So if I say, hey, can you find the velocity at t equals t, instantaneous velocity at t equals t, that means at that particular second, at the first second, when t equals 1, I want the velocity at that particular moment. Can you calculate it for me? And the answer is yes, we can actually calculate it. And fortunately, we don't need to repeat this infinite times, by shrinking the interval even more small, even smaller. What we can do, we can find the tangent line. Now, what does the tangent line, or rather, how can we find the tangent line? Again, you have 2 points. If you just merge it with one another, I mean, if you just close it down, if you shrink the difference, the interval, to really small, that means it will look like that the 2 points have merged onto each other. Then you will see, or you can eyeball only one point, which is just touching the graph, which is not intersecting the graph. It will just touch the graph at that point and move on. That particular point will give you the instantaneous value. On this occasion, it will be velocity. It will not be velocity all the time, but for this particular example, it will be velocity. And that line, that straight line touching that graph at that point will be the tangent line. Okay. Here you go. Where is that? Excuse me. Yeah. So this is the graph I was talking about. You just shrink the interval. You just start taking smaller values, smaller differences, like this, like in the second graph. You can see initially it was 1.5 and 1. You can see we have changed it to 1.1, and you can see the difference is really small, right? It's even hard to eyeball it. And you can clearly imagine I can easily, at least mathematically, not in graph maybe, I can easily decrease the difference. I can easily take it 1.00001. Maybe I wouldn't be able to graph it separately from 1, but I can definitely do that mathematically, right? So it says as the interval on the t-axis shrinks, the slope of the secant line approaches the slope of the tangent line. We already know the definition of slope, right? It's the differences of the functional value or the dependent variable over the independent variable, rise over run, or however you want to remember. So as the interval is getting shrink, right? The slope of the secant line and the slope of the tangent line you'll see it will get closer to each other, and soon it will merge. I mean, 2 points will merge onto each other and we'll get our tangent line. Where is that? Here you go. So how can you do that? What's the mathematical way of doing that? And why? The question could be, why do we need that? We're trying to discuss limit. Why are we here, right? That could be the question. And now we want to see, why do you need this idea for going to the concept of limit? Okay, here we are. So as you can see, we have only 1 point right here at t equals 1, and we also have the corresponding value, which is 80. But as I said, we want to know the instantaneous value at that particular moment. What happened at that particular second? This 80 might confuse you. You might say, hey, we don't even need to calculate it. It looks like the answer is 80, right? Because it is the functional value. For t equals 1, we get 80. So isn't it the instantaneous value? Isn't it the value you're looking for? It might confuse you. No, the answer is no. It is definitely the corresponding functional value, no doubts on that. But as I said, we are looking for the instant value at that particular moment. And for that, you actually need 2 points really, really close to each other, probably the smallest you can imagine, and then you need to calculate it so that you get the most probable, most possible, most accurate possible number. And for that, we use the idea of limit. And what is that? So since we are looking for the instantaneous value at 1, what we do, we say, or rather we set up limit as t tends to 1. Now, what does this word tends to mean? Anyone? Don't worry about the mathematical definition of it. What do you understand, or what do you get when you first hear this word tends to?
Approaches.
Approaches, very good. Anyone else?
Move towards.
Sorry?
Moving towards.
Okay, moving toward. Okay, yeah, very good. Okay, yeah. So since we're looking for, as I said, we're looking for a value at a particular point, we'll approach to that point. And we'll approach really, really close to that point and see what does it give us. And that's why the idea of limit comes into this. So how should we do that? Okay, so wherever we're trying to find the limiting value, we actually say the value is going towards that or approaching that value, and there we're trying to find the value. Oh, where is that? There. Yeah, here you go. Limit t tends to 1. That means the value t is moving towards 1. It's going really, really, really close to that. Okay. And at that particular t, at that particular value point, we want to see the what it gives us, what is the corresponding value of it, which gives us 64. And we have already seen it when we started, if you remember. Where is that? Oh, here it is. You can see the smaller the difference is getting, you can see it's getting really, 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 really close to 64, right? The difference is really, really close to 0 because we are trying to find the value at 1. So the interval, as you can see, the last 2 or 3 intervals, as you can see, as I'm approaching towards more towards 1, you can see the value is getting more towards 64. Can you see that? And the fun fact here is if you increase this number of zeros here, for example, if you take 1.0000000 10 zeros, then 1, you'll still see this value will not be more than 64. It will still be 63.9999, something like that. It will not go, it will not reach the value 64. Since we are not really taking 1 and 1 here, we are trying to calculate the smallest possible time difference and their corresponding value. So we'll have a value here which is really close to 1. This value you will see will be really close to 64. It will never reach 64, but it will be really close to 64. That's why we say the limiting value, I mean, when t tends to 1, t tends to a particular value, this will be our corresponding limiting value.
I have a question about that.
Sure.
So, so you have it like that 1 approaching, like or going almost to 1. Will it be the same if we're using, I guess, like 0.999999 going almost 1? The same how we have 1.000001 or whatever?
Yeah, I think you will definitely get something similar. Yeah, and you can obviously try that. You just try to put, let's say, 0.99998 in the function. You'll see it will be close to 64. I'm pretty sure. I mean, mathematically, it's already giving us an idea. Yeah, you're right. Since we are approaching to 1, it will definitely be pretty close to 64 as well. Yeah. Very good question, by the way. I actually would have gone to that. But yeah, good point. But you will see it will not reach the digit 4 here. I mean, it will not be 64 here. It will be always 63 point something. Since you're approaching towards 1, you will see, doesn't matter how big, I mean, how small, rather, I'd say, the difference you take, it will never cross 64. It will appear that it might go 64 someday, but it will never exceed 63 point something. It will be always close to, pretty close to 64. Even this one, you can round it to 64, right? Can you? Right? Can't you? Because it's more than 5. I mean, it's more than 63.5. So you can actually round it to the next whole number, which is 64. And same as this one, same for this one. for all of this, you can round it to 64, but as you can see, it never reaches 64. The idea of limit is really, really interesting and really beautiful. You'll see more examples of it. But before that, any question from this? We'll see more examples, so don't get demoralized if you don't understand it. We'll see more examples and it will definitely make more sense. But as of now, any question up to this? Anything you want me to rediscuss? Anything that's not convincing enough? I'm more than happy to rediscuss it. Oops, someone has left the meeting. I can see one less in the participants list. Anyway, no problem. Maybe he or she has a particular reason to leave.
I have one question for
Yeah,
you.
sure.
Do we have to go and find the slope of like 1-to-1, or can we go straight to the tangent slope if that's what the question's asking?
Yeah, you can go straight into the tangent line. I mean, we're trying to build up the idea. That's why we are showing it this way. But when you face this type of question in the homework or in the exam, you'll straight away calculate it. You don't need to show all this stuff, all these steps. It will either say find the slope of the tangent line or find the slope of the secant line. It will straight away tell you to find the value. Okay, no other questions? Anyone? All right, so let's.
Well, actually, I had a question. Will we be learning how to get the slope and equation of the tangent and secant lines in a later lesson?
Yeah, hopefully we'll do it today. We still have plenty of time.
Okay.
We'll definitely start it, but I'm not sure how much we'll be able to finish. But yeah, we'll definitely start it. And this is the next thing I'll actually do. Go to the next slide. Yeah. Oops, sorry. Yeah, definition of limit. Okay, we'll start with this. And the agony is when you go over the definitions, go over the theories, it often looks clumsy. It often doesn't make sense. But when you actually do one or two problems, then it makes more sense. Then you'll start getting the things. That's what happens with me as well. So bear with me. Hopefully, when you do one or two maths, one or two problems, hopefully it will make more sense. If it doesn't, I'll try to rediscuss it and try to convince you anyway. Will you be able to post the slides on Canvas as well? Yeah, I'll definitely do that. I'll actually do that once. Yeah, I think I can start doing that from today. If not, I'll definitely start doing it from tomorrow. Yeah. The problem is I don't have a laptop here, so I couldn't bring any. I actually had a plan to return on 22nd, but I had to stay for some reasons here, and the next flight is tomorrow, so I'll definitely return tomorrow, hopefully, and things will be much better for me because I have my own setup in my apartment, so it will be much more convenient for me. Thank you for bearing with me, and I apologize for this inconvenience. Okay. Okay, the definition. So again, you don't need to memorize the definition. I don't like the idea of memorizing, but yeah, it's better if you remember what it actually means. Okay, if you remember how does it work, or what does the definition signify, then I think it's fine. Okay. All right, so let's see the definition. So suppose the function f is defined for all x near a except possibly at a. Now, what does it mean? Near a, but except possibly at a. What does it mean? We'll see graphically. I will see what does it mean graphically, and hopefully it will be easier for you to visualize this. Let's finish the definition first. And now it says if the function is arbitrarily close to L is any value, so don't bother. So it's arbitrarily close to any value for all x. Okay, sufficiently close but not equal to a. Then we say the limit of that function f of x when x tends to, this means tends to, so the limiting value of that function f when x tends to a is L. And we say the limit of the function is L when x approaches a. That means when x tends to a, if x approaches a, the limit of the function f is L. Now, if we go back to the previous slide, here you go. Limit t tends to 1, that means t, where is the interval? Here you go. The value of t here is very close to t, but as you can see in the definition, it's not equal to a, where a on this example is 1. So you can see the value is very close to 1, but not exactly equal to 1, is it? Not really. It's not exactly 1, but it's really close. So that's what the definition says. X is really close to a, but not equal to a. Same goes for this one. T is really close to 1, but not equal to 1. And then whatever the value gives you, again, this functional value will be pretty close to L. Okay. Whatever the value L is, doesn't matter. It will be different in different for different functions. So this functional value will be pretty close to L, and then we say the limit of this function is L. So for example, this one, our functional value, as you can see, it's getting pretty close to 64, right? It's going more and more towards 64. So that's why I say our limit for this function is L, I mean, is 64 for this function. I'm sorry, my voice is getting lower and lower because I've been talking for 2 hours now. So I apologize for that. If you can't understand any of the words I say, don't hesitate. Okay, just let me know. I'll try to say it again. Okay, so let's go back to the definition again. Yeah. Any question from the definition? Anything you want me to rediscuss? Again, when you solve a couple of problems, it will surely make more sense, and then you will see what does this A and L actually signify. What do they mean? You will definitely know once hopefully we can do at least one example today, but let me see if you have any question first. Anyone, any question?
Just to clarify, so A is, I guess, the number in question, like the other one will be 1, and then X would be some arbitrary value that we choose, right?
So yeah, A is definitely the value will be approaching towards. This will be given, and X, we don't need to choose it. X is the independent variable of uh, the given function. I mean, if it's f of x, then we say the independent variable is x, right? But for the previous problem, we had s of t, I believe. Where is that? Yeah, you can see the function was s of t. So the independent variable was t. That's why we have used t here. Can you see that? So we don't need to choose anything. We just need to eyeball the function and see what is the independent variable. Whatever it is, we can use it here. For s of t, we have used t. For f of x, we have used x. So whatever it is, whatever we have here as the independent variable, this guy, I mean this variable will be used here.
Okay, that makes sense.
Mhm. Anything else? Any other questions? Anyone? Am I going too fast?
No, it's a good pace.
Yeah, just let me know, okay? I can't really slow down too much, but I don't want to be, you know, going too fast, because if I go too fast, we'll probably miss one or two contents. You'll miss some of the topics, some of the uh, concepts. So I don't want to do that either. Okay, so looks like there is no other question. Let's see whether we can do one example. Yeah, I think we can do this one. Yeah. Okay, so here is the graph of, I guess it's, oh, they haven't written the function here. Sorry about that. I think I have it here. Yeah, it's the function is square root of x minus 1 over x minus 1. Okay, just remember this function, square root of x minus 1 over x minus 1, and this is the graph of it. This is the graph of this function. Okay, first I want to discuss why does this graph look like this, because we can see a curve. We can also see a black hole here, or not hole, black dot here. Now what does this mean? Anyone? Is there anyone who is familiar with this type of graph? I'll discuss it anyway, but if anyone is familiar with this, it will be more interesting because you can actually contribute to the discussion.
I don't remember the actual name of the dots, but essentially it's that the graph is correct for in all places except for those dots. If I probably don't remember this right, but it's basically a break in the graph where x can't equal that number, if I remember right.
Yeah, exactly. Very good. Yep. So mathematically, we say that this graph, or rather I should say this function is mathematically defined at all places apart from these holes, apart from these white holes. Okay, the function is not defined in these two places, but we do have a defined value at x equals 2. Oh, okay, I think it's not the graph of that function. Yeah, I don't think it's the graph of that function, because this graph should have a value at x equals 3. This doesn't have a value at x equals 3. So yeah, I think it's not the graph of that function. Anyway, we can discuss this particular function, whatever the function is. It's not written though, but it's not necessary. We can discuss the idea here. Okay. So where is that again? Yeah. So this black circle means we do have a defined value at x equals 2, but it's not on this curve. That means there's a break. Now, what does a break mean? That means we actually have a piecewise function. Now, is there anyone who has heard this word before, piecewise? Anyone?
Yes, I have it. I heard about it in algebra.
Algebra, okay. Anyone else? Piecewise function? If you haven't, no worries.
Heard of it, but I just don't remember what it is.
Yeah, no problem, no problem. We'll actually go into that. So piecewise function is, you can clearly understand by the way I have said it, piecewise. That means you will have more than one piece for that function. So if you go back to the previous function, let me go back to that. Where is that? Oh, here you go. So for this function, you can see we only have one piece. S of t equals something, right? We don't have excuse me, we don't have anything else. This function has only one part, which is negative 16t squared plus 96t, right? So it's a usual function. But if we have a function which has more than one part, like for example, s of t equals this for some x and another part for some other x. That means we'll have more than one part for the function. I wish I could write it for you, but let me show it on Google. I apologize for that. Hopefully I'll fix it once I arrive Laramie, and it will be definitely fixed. It's already there. Let me show one example of it. Can you see the screen?
Yeah.
Okay, here you go. So this function f of x, you can see it has 3 parts instead of 1, like the way we had for the problem we have just solved. For this function, you can see we have 3 different parts, and all of these, for all of these, we have a certain value of x. That means only when x is less than 2, our function will be x plus 3. If x is in between negative 2 and 3, our function will be negative absolute value of x plus 5. And when x is greater than 3, I mean, whatever it is, if it's more than 3, equal or more than 3, then the function will be defined as x minus 4. So for certain x, we have a certain part of the graph of the function. And the graph looks like this as well. You can see it's the graph of the same function, but you can see we have 3 different parts, right? So for this x, we have the red one. For this x, we have the blue one. And for this x, we have the greenish one, the olive green, you might say. So this is how you define a piecewise function. That means you'll have more than one piece. You'll have certain values of the independent variable. And for that, you have a corresponding function to define. Here you go, like this one, we have 3 parts. So this is how a piecewise function look like. And if we go back to the problem, so this function actually is a piecewise function. So for x equals all the x apart from 2 and 3, the function is this, the curve, and the other part is for x equals 2. For x equals 2, the function is this particular point. It doesn't need to be curve or straight line all the time. It could be a single point. For example, for this particular function, for x equals 2, our function is 5, as you can see. It goes straight towards 5, right? If you draw a straight line, you will see it goes to 5. That means the piecewise function is for x equals, for all the x apart from 2 and 3, the function is this curve, whatever the curve is, it's not really given. And for x equals 2, it will be 5. So clearly you can see it's a piecewise function, right? And at x equals 2 and 3, as I said, there's a break. That means the function is not defined there. Although we have a defined separate value at x equals 2, but we have nothing at x equals 3. There's a break. So that means you can come up to 3, then at 3 you don't have anything, then after you cross 3 you again have the function. At 3 you don't have anything. Okay, at 2 again, if you approach towards 2, you have values like this in this curve. At 2 you don't have a value here, but you have a jump. If you jump to 5, you can see there is a defined value. Again, if you cross 2, you'll again come back to here and you have defined value up to 3. This is how a piecewise function looks like. Okay. All right, so